Hello everyone, I'm Aayush Modani and my project partner is Mandar Raje, and we are doing the project called block matching using SAD algorithm, which stands for sum of absolute differences. In this part of the video, we are going to implement the project on FPGA. So we'll start with creating a new project in Quartus. Click on next. Select the directory where you want to create the project. I'll create it inside projects folder and create a new folder called SAD. I will give the name of the project as project underscore quartus underscore SAD. And the name of the top level design entity will be project underscore qsys underscore scrad. Click on next. Since I do not have any files to add, I just click on next. I am using D1 board which has Cyclone 2 FPGA. It has a pin count of 484 pins and speed grade of 7, and then select the EE278 484C7 version. Click on next. Select the simulator as Model Sim by Altera and language is VHDL. Click on next and finish. Now we have to add components. We'll design the system in qsys. qsys is a system building software. We will add all the components. We'll add components such as NEOS processor, JTAG UART, performance counter, PLL for SDRAM, and our hardware accelerator. I'll start with the NEOS 2 processor. Select the component, add NEOS 2 processor. I will use the economy version. Then add the JTAG UART. No need to change the settings. Click on finish. Next, I will be adding the SDRAM. So select SDRAM controller, and we'll be using the data width as 16 bits. Finish. We need a clock PLL for this SDRAM. So I'll select the clock module for the D1 boards. So select D1 board, and we'll be using the clocks only for SDRAM. No video or audio in this project is required. And I also need a performance counter. So select the performance counter unit. Good to go. And now all the components that we need are present. So we'll give the clock, reset, and other signals. First I'll give the clock. The clock from the primary clock is given to the clock of the PLL. The PLL generates another clock which is given to all the other components. Next we'll give the reset signal of the primary clock to all the components. We also need to give the reset signal from the NEOS 2 processor to all the components. we will be fetching the instruction and data memory from the SDRAM, so I'll select both, and only the data from other components. Now you can see there are some errors, so we'll assign the base address and most of the errors are gone. Now in the NEOS 2 processor we need to give the reset and the exception vector memory, so we'll select SDRAM. So all the errors are gone. Now we need to remove the warning. So we forgot to give the interrupt. We'll select the interrupt pin, and we also need to export the conduit wire of the SDRAM controller and the SDRAM clock. So we'll give this name as DRAM and DRAM underscore clock. Now we can save the system. I'll give the name as project underscore qsys underscore sad. Remember, we gave the same name while creating the project. So click on save. Now we need to add the hardware accelerator, so I'll create a new component. I'll give it name as hardware underscore accelerator. I'll give the same name for the display name. Now I need to add the file, so I already have the file. I'll just add it. It is present in one of the other folders called files. I'll select the Verilog file, click open. Now we need to analyze the files. Now we can also change the parameters. These are the parameters which I had written in the code, and these are the signal types: clock, reset, read data, and others. So these are assigned to the Avalon memory map interface. We need to associate the clock and the reset signal, so we'll associate the clock, and we'll also associate the reset signal. So all the errors and warnings are gone. Click on finish, save the system, and our system is built. Now we need to add the hardware accelerator that we generated just now. So I'll add the hardware accelerator, will not change the parameters. Now the accelerator has been added. I'll give the clock and the reset and the data master pins. Now system is finally built. Click on save. Now we can go to generation tab, select Verilog, and then click on generate. So this will generate a QIP file which can be used by the Quartus. So in this process we are instantiating the IP files given by Altera, and they are going to be used in our project. So this process will take some time, and after that we will import the files using the QIP file in our Quartus project. The system has been generated. Now we'll open Quartus, go to Files tab, and we'll add the QIP file. First click on file name, select IP variation files. It is inside the SAD project versus SAD folder in synthesis. Just select the QIP file, add, apply, OK. Now we need to assign the pins. We'll use the import assignment editor, and I already have the file with me, so I'll just select the file. It is called QSF file. OK. Now just to check, I'll go to the assignment editor. All the files, all the pins, locations have been added. Now we can compile the system. So what I did was I took the QIP file, the CSV file from Altera, and for the DE1 board, and using that file I changed the name of some of the signals, such as for the DRAM, HDRAM, and I got the file and I imported it. The compilation will take some time. So the compilation is complete and the entire system is built. Now we can download it onto our D1 board. I will click on OK. Open the programmer. It is called USB Blaster. Select USB Blaster if it is already not selected. Now we need to add the file. It is called SOF file. It's inside the output files folder, and program the system. Now programming has been completed. I'll save the chain file. Now you can see all the inputs and output have been assigned. We'll go to Eclipse. In Eclipse we can write the C code. We need to select the workspace. I'll select the same folder which was used to build the juices and quarters files. Inside the SAD folder, I'll create another folder called software. Okay. So first we'll use a template by Altera to display hello world using Neos. I'll create a new project from BSP and Neos2 and BSP application. I'll use the same SOPC file, SOPC info file. So the SOPC info file contains the information about the components that we used. It is inside the SAD folder. It may take some time. I'll give the name of the project. It is project underscore neos underscore SAD. I'll use the default location and select hello world small because it takes less space on the board. So finish. So it will create a template file, template C file to print hello world using Neos2 processor. First we need to build the system. This is the hello world C code which is generated using the template. Here is the main code, and build this project. Building of this project is taking time. After the building is complete, we can run it as Neos2 hardware. So it will process the C code on the D1 board, and after that it should print hello world from Neos2. As you can see, it has printed hello from Neos2. So our project building has been successfully completed. Now I will I've already written my code. I'll just copy it and paste it on the Eclipse, and this is my code. This is the block matching algorithm code written in C. For the performance counter, the base address, we can see it from the juices. It is 100, 1000 in hex, and for hardware accelerated it is 0 in hex. So I need to change it in my code. 0. I'll save the file, and this is my entire code. This is 64 by 64 frame for previous and current frame, the array for that, and the rest of the code. So first I'll start the performance counter, and after that the main code. So inside that I'm running nested loops, and then I'll send the values of the current and the previous frame from the C code to the Verilog code using the IOWrite, and read it using the IORead function, and this calculates my sum of absolute differences value, SAD, and I'll end the performance counter, print the motion vector values and the SAD values, and print the performance counter value. So I can run the system. So I have given the same value for the previous and the current frame, so we expect the SAD value to be 0. This is the output. I'll maximize it so that we can see the output values, and we got the correct values for SAD, that is zeros. Thank you for watching.